to the 8th session on electrolytic conductance. We have been seeing the applications of conductance measurements and we are going to continue that. We have been dealing with applications of Cauchy law, and here we are going to see another application of Cauchy law, that is in the determination of ionic product of water. Now, let us see what is ionic product of water. Ionic product of water at a given temperature is a product of molar concentrations of H plus and OH minus ions. That is Kw, that is the notation used for ionic product of water, is equal to molar concentration of H plus into molar concentration of OH minus ions. Here, to calculate this, we have to know the ionic conductances of H plus, ionic conductances of OH minus, as well as the specific conductance of water. Here, you can see the values are provided, and from this we are going to calculate the lambda 0 value for water by summing up the ionic conductance of H plus and OH minus ions. Since the values are given, I will add up 349.8 plus 198.5, and adding together you get it as 548.3, and the unit is ohm inverse centimeter square. Kappa, that is a specific conductance of water, is given, which is equal to 5.54 into 10 to the power minus 8 ohm inverse centimeter inverse. Lambda 0 m, we know it is a molar conductance at infinite dilution, is equal to kappa into V, and V, it is the volume containing 1 mole of water. It is a volume containing 1 mole of water. So, this volume V, which contains 1 mole of water, is equal to lambda 0 m by kappa. By rearranging this, that is kappa comes to the denominator. Now, substituting these two values, lambda 0 m is, we have calculated using Cauchy's law, that is 548.3 divided by kappa, which is given 5.54 into 10 to the power minus 8. So much centimeter cube will be the volume occupied by 1 mole of water. Now, if you have to find out the number of moles occupying a particular volume, we know that 1 mole of water requires so much volume, so much centimeter cube. So, how much moles will be there per centimeter cube? That will be, because we are having only 1 mole, so that will be equal to 1 mole divided by volume containing 1 mole, and that is the value given here. So, this becomes reciprocal, and therefore, just inverting that fraction, 5.54 into 10 to the power minus 8 divided by 548.3 will be the number of moles which occupies in 1 centimeter cube of the electrolyte. That is, here it is water, and the value is 1.01 into 10 to the power minus 10 moles. Now, this is for 1 centimeter cube. If you have to convert that into decimeter cube or decimeter cube, we are converting it because molar concentrations are represented in moles per decimeter cube, or you can call it as moles per liter. Now, converting this into moles per decimeter cube, you have to multiply it with 10 to the power 3, and therefore, this becomes 1.01 into 10 to the power minus 7 moles per decimeter cube. Now, this is the number of moles of water. Number of moles of water is 1.01 into 10 to the power minus 7 moles per decimeter cube. We know that from 1 mole of water, you have 1 mole of H plus ions and 1 mole of OH minus. What does it mean? If you take 1 mole, here also you will be getting 1 mole each. So, whatever is the molar concentration of water, the same will be the concentration of H plus ions and OH minus ions. And therefore, you can substitute for ionic product of water as Kw is equal to molar concentration of H plus into molar concentration of OH minus, and the value is 1.01 into 10 to the power minus 7 moles per decimeter cube for H plus, and same is that for OH minus. So, again multiplied by 1.01 into 10 to the power minus 7 moles per decimeter cube, which makes the value as 1.02 into 10 to the power minus 14 moles square per decimeter raised to 6, because here we have moles multiplied by moles, it becomes square, decimeter cube and decimeter cube becomes decimeter raised to 6, or approximately we usually write it as 1 into 10 to the power minus 14 mole square decimeter raised to minus 6. This is what we say, it is a ionic product of water. And just like equilibrium constant, this is dependent on temperature, and the temperature taken is at 25 degree Celsius. Once the temperature is changed, the value of Kw also changes. So, with this we finish the applications depending on Kohlrausch's law. Next, we are going for the measurement of conductances, and here we have conductometric titrations. You all know the volumetric titrations, in which we measure the volume and then take the quantitative results from that. Here in conductometric titrations, there is a difference. We will be measuring the conductance with respect to volume of a titrant added, and then we plot a graph with volume of titrant and conductance, where we will be getting two straight lines, and the intersection of these two straight lines gives you the equivalence point. And this is because conductance of any substance depends upon number of ions as well as the speed of the ions. And therefore, here when we say equivalence point, that is totally different from end point what we measure in a volumetric analysis. Equivalence point is the exact neutralization between, if you are taking an acid and a base, acid versus base. Okay. Here there is the exact neutralization of an acid by the base, nothing is in excess, neither the acid or the base, and this point is known as equivalence point. In volumetric analysis, what we get is either we will be adding acid from the burette and base is taken in the conical flask, we take an endpoint in which an acid is in slight excess. So, you call that to be an endpoint, and in this case it is known as the equivalence point. So, conductometric titrations gives us equivalent points. Now, the setup for this is like this. You have a beaker in which you take the alkali, in which we are keeping a conductivity meter, to which a conductivity cell, this is a conductivity cell dipped in it. Okay. And it is read from the conductivity meter, the conductance you will be getting. HCl is added from the burette, and during the titration the temperature is kept constant. Either you can keep it in a thermostat or you can keep it in the room temperature condition if there is no much variation. Here we will be seeing different types of titrations. First one is the acid alkali titration. Normally we do it in a volumetric, and in this case it is slightly different, we are measuring the conductance. Now, in an acid alkali titration, a volume of the acid is taken in the titration cell, it is taken in the titration cell, and conductance is measured. Okay. Now, vessel contains acid, and this will be acid, and you will be adding alkali using a micro burette. because we have to take small volumes, and to be more accurate we use a microburette. Now, the alkali, unlike in a volumetric analysis, we have to take the alkali or any electrolyte which is taken in the burette to be 10 to 100 times stronger than that is in the conductance vessel. Now, what is the reason for that? When we add alkali to acid or any titrant is added, the volume here keeps on increasing. When volume increases, what happens? The interanic attraction decreases and thereby the conductance increases. So, the conductance change is not totally depend on the titration, but also on dilution. To prevent that, we take the alkali in the burette or any other electrolyte taken in the burette to be 10 to 100 times concentrated, and therefore, we require only very few volume of the titrant, so that equivalence point is reached. Okay. Now, it is added in fractions, conductance is plotted against the volume of alkali to find out the equivalence point. Now, let us see how the titration goes on. So, first example is strong acid and a strong base titration. So, let us take a strong acid to be HCl and a strong base to be NaOH. Okay. And finally, you will be getting NaCl plus water. So, this is a neutralization reaction in which acid is taken in the conductometric cell and NaOH, I am just putting it in the bracket to show that it is actually not in the medium, it is added from the burette. Okay. So, first we will take HCl, we will measure the conductance. We add NaOH in, it can be either in 1 ml portions or it can be 0.5 ml portions, it depends. That is depending upon the concentration of NaOH you have taken, whether it is 10 times or it is 100 times. So, 1 ml portions you will be adding, you will measure after each addition, you will measure the conductance, then again next addition is done and we will continue for that. So, first what happens is, when HCl reacts with NaOH for the first 1 ml, what happens is NaOH is not in the medium, whatever it comes to the medium reacts with HCl and gets converted into NaCl and water. Water is not that ionized, HCl is ionized, which will be in the titration cell. NaCl is completely ionized because that is also a strong electrolyte, but NaOH does not come in the medium until unless the equivalence point is crossed. So, here what happens is, actually before equivalence point you have HCl and once the NaOH comes in, HCl is changed to NaCl. Here chloride ions are in common, or you can say that H plus ions are replaced by Na plus ions, right. H plus ions, they are fast moving ions, they are replaced by Na plus ions which are not that fast, and therefore, what happens to the value of conductance, it keeps on decreasing. Once the equivalence point is over, because there is no HCl remaining, you will be having excess NaOH. And from NaOH, it is a strong electrolyte, you have fast moving OH minus ions, and thereby on each addition you can have an increase in conductance going on. So, after equivalence point it keeps on increasing. Just refer the graph. See, this is the volume of alkali and here we measure the conductance, and first the conductance decreases and then conductance increases. You draw both straight lines, it meets at a point, and this point is known as the equivalence point. Okay. So, here we need not wait for whether it is nearing the end point or not. We have to cross the end point and take the values, and therefore, no precautions has to be taken near the equivalence point. Now, let us consider in a similar way weak acid and a strong base. Weak acid, you can take acetic acid as an example, and then strong base is NaOH, and you will get the product as CH3COONA plus water. In this case, this is a strong electrolyte. This is a strong electrolyte, but it is added from the burette. So, it is not in the medium, and this is a weak electrolyte. So, weak electrolyte has got very little conductance. Once it has been converted into strong electrolyte, its conductance increases, okay. And after the equivalence point, you have excess of NaOH with the fast moving hydroxyl ions, okay, and then conductance increases steeply. Now, extend the two lines, and the intersection of the 2 points will give you the equivalence point, and thereby you can determine the equivalence point, from which you get the volume, and naturally you can, from that you can calculate the concentration of whatever is unknown. Next is strong acid and a weak base. You can take strong acid at HCl, weak base is ammonium hydroxide, because that is what is shown here in the graph. You will have ammonium chloride plus water. Okay. Now, this we are going to add from the burette. So, I am putting it in the bracket. These are strong electrolytes. Okay. So, HCl being a strong electrolyte, it has got a high conductance value, but when ammonium chloride is added, it gets converted into ammonium chloride. That is, instead of H plus ion, you are going to have ammonium ion, which is slower than H plus ion, and therefore, the conductance decreases. You can see it from here, it decreases. And after the end point, you have ammonium hydroxide in excess. That is, excess of ammonium hydroxide means this is a weak electrolyte, and therefore, its conductance is low, and therefore, here we do not have much change in conductance in addition of ammonium hydroxide, because it is a weak electrolyte. We can say it as a weak base, and therefore, you get a straight line parallel to x axis, and again from the intersection of the point you will get the equivalence point, just like what we get from a volumetric, and from that you make the calculations based on N1 V1 is equal to N2 V2 and so on, and find the normality or mass per liter, whatever is required. Next one is conductometric titrations, where both acid and base are weak. Now, in this case you should note the point, such titrations cannot be done in a volumetric experiment, but this can be conducted in a conductometric titrations. Now, let us consider a weak acid, take acetic acid CH3COOH plus a weak base, that is ammonium hydroxide, which is added from the burette, and you have CH3COONH4 plus water, that is ammonium acetate and water. Here it is a weak acid. Ammonium acetate, it feebly, because it is a salt, it feebly ionizes, and therefore, it is better than acetic acid, and therefore, the conductance should increase. But again, after the equivalence point, you have excess of ammonium hydroxide, which is a weak base, it is a weak base, and therefore, the conductance remains as such. So, again you have a straight line parallel to the x axis. Now, in the beginning you can see there is a dip in the curve. This is because we add ammonium hydroxide to acetic acid, ammonium acetate is formed, which is ionized as acetate and ammonium ions. This prevents the ionization of acetic acid and ammonium hydroxide due to common ion effect. You can see CH3CO minus is an ion present in acetic acid, which is also there in ammonium acetate. Similarly, ammonium hydroxide added will have a delay in ionizing because it has got ammonium ions in ammonium acetate, and therefore, first it shows a slight decrease and then it keeps on increasing. Again, the intersection of the point will give you the equivalence point, from which you can calculate either the normality or mass per liter of any of the unknown solution. Next is precipitation titrations. Here again it is very difficult to do it in a volumetric experiment, because due to precipitation the color of the indicator will not be sharp. So, in this case again we can do it in a conductometric way, where we take the precipitation of potassium chloride, which contains a chloride ion, with silver nitrate, which is added from the burette, and you will be getting the product as potassium nitrate and silver chloride. Now, silver chloride, you know, it is a solid, it gets precipitated as a white curdy precipitate, which you will be doing in chloride detections. Here potassium chloride is a strong electrolyte which is completely ionized, and potassium nitrate, which is formed by the addition of silver nitrate, is also strong electrolyte, and so that will be completely ionized. Silver nitrate will be in excess only after the equivalence point. Now, in the medium, in the reaction vessel, you will be having potassium chloride, and when we add silver nitrate, this potassium chloride, each of the molecules, they get converted into potassium nitrate. Here, when we compare the conductance of KCl and potassium nitrate, they are almost equal. Equal value for conductance, and therefore, there is no much change. So, you have a line, it goes on straight parallel to x axis, because there is no much change in the conductance while KCl is converted into potassium nitrate. Now, after the equivalence point, you have excess of silver nitrate, which is again a strong electrolyte. Okay? And therefore, silver ions and nitrate ions are brought into the solution, and therefore, it increases steeply. Now, again intersection of these two lines will give you the equivalence point. You can find out the volume of silver nitrate used, and from that, using the relation N1V1 is equal to N2V2, you can calculate the concentration of either chloride ions or KCl, or it can be used for determining the concentration of nitric acid also. Now, let us see what are the advantages of conductometric titrations. Titrations of colored solutions, for which ordinary indicators cannot be used, can be successfully carried out conductometrically, because here we need not wait for the equivalence point or the end point. We do not determine it visually. What we do is we determine it is graphically. Second point is conductometric titrations can be carried out with very dilute solutions. Here, for very dilute solutions, the indicators cannot give sharp colors. It will be giving only a faint color, and it will be very difficult to determine the end point. While for conductometric titrations, we can take dilute solutions also for titrations, and they give better results, because we know that in dilute solutions the deviations are least from ideal behavior. Third point is it can be used for titration of weak acids and weak bases, which cannot be carried out by normal volumetric procedure. We have already seen it, because for weak acid, weak base titrations, there are no good indicators that can show a sharp change in color at the end point. Fourth point is it is used for studying the precipitation titrations or any precipitation reactions. Again, here also we do not need an indicator, and it can be studied properly. And last one in this method you get the equivalence point which is detected graphically. So, we need not give attention like whether the equivalence point is being reached or is it being it is over or anything of that sort. Just carry out the reaction, let it go on, you measure the conductance and you determine the equivalence point by graphical method. Now, to conclude, let us just brief the points. That is, first we have been determining ionic product of water, and ionic product of water Kw is equal to product of ionic concentration of H plus ions and ionic concentration, molar ionic concentration of OH minus, and it is temperature dependent at a given temperature. Temperature should be constant. Next, that is from Colrausch's law. Next is conductometric titrations, in which we had been seeing acid alkali titrations of both strong acid and strong base, strong acid and weak base, weak acid and strong base, as well as weak acid and weak base. It was also used for precipitation titrations too, in which we can't have a good end point when we do it in volumetric method. Conductometric titrations give good results with respect to precipitation titrations. Thank you.